right? Now, before we start, a few announcements that I have posted 2 other tutorials for you. And for some reason, I have seen only one of you have submitted a tutorial and the others have not. So I'm not sure about the reason, and I will extend that for maybe 2 days further until Wednesday, so that everyone can submit. And these 3 tutorials are actually based on around the first 30 lectures that you have for astronomy, right? Most of the things. So make sure that you complete it, because I am planning to give you another 1 or 2 tutorials based on this part that we are doing for the cosmology, which is the second set of lectures that you have. So make sure that you submit those 3 tutorials by July 17th. And as far as I know, yes, it should be July 17th. And then we will discuss those tutorials on one day. And most of these questions are based on astronomy lectures, so it shouldn't be that much hard for you to complete this. And then I will be, so you will get another 1 or 2 tutorials based on this part for general theory of relativity, which I will be discussing towards the end of your course, right? Right, so let me share the screen, and I can still there are 4 of you are missing here. It's not here. K.V.S is here. Right, so I guess Eno is not here. Okay, right, I guess Navini and Sajini is also not here as well. And then maybe Tamil is here, right? Anyway, so let me share the screen with you and start. So I have shared the lesson 5 with you, and so I hope all of you can we see the screen, right? With lesson 5, general theory of relativity. Can one of you confirm me whether you can see the shared screen or not?
Yes, sir. You can see it.
You can see it, right? Okay, sir?
Yes. Yes.
Okay, right. Thank you. Now, remember up to the last week, so what we have done is we just build up all the mathematics that we need to know in order to identify, in order to understand this general theory of relativity, right? Now, today what we are going to discuss is how to understand this Einstein's field equation, which is the final result of what we have done up to now. And then we will be discussing different applications of Einstein's field equation, right? Now, so there are basically 3 key principles that lead to Einstein to develop his theory. And these three principles, number one is called as principle of equivalence. And the second one is called as principle of general covariance. And the third one is called principle of consistency. So his idea of building up his theory was based on these three key principles, right? Now let's look at one by one to see what these principles mean, and then we will move into derive. Actually, not derive. We will discuss how Einstein, approach to his Einstein field equations at the end, right? Now, the first one is called as principle of equivalent. Now, what that means is, now if you consider, so let me discuss one of the thought experiments that Einstein did to understand this concept. So the first thought experiment. So consider an elevator, right? So if you consider an elevator which is resting on the surface of the earth, so consider, I expect that maybe most of you have experienced this, right? Using an elevator. Now, if you consider an elevator which is resting on the surface of the earth, so the elevator is not moving, just resting on the surface of the earth. Now, if you are inside this elevator, what would happen is you or any other observer, he will experience the gravity pulling him down, right? So this is just the general scenario. So if you are on an elevator which is at rest on the surface of the earth, what you will observe is you will experience the gravity which is pulling you down, right? So that's what will happen, right? And the second scenario is if you consider an elevator which is in deep space away from gravitational forces, but is undergoing a constant upward acceleration. Now, this is the second scenario. Remember, all these four scenarios are kind of related to different different instances about an elevator, right? Now, if you consider an elevator which is in a deep space away from gravitational forces, now the idea is when you go into this deep space, you can kind of assume that you are in a Minkowski space or a flat space, right? Which means you are away from all the gravitational forces, and because of that, the space is not curved, right? According to Einstein, and because of that, you can kind of assume that you are in a Minkowski space, which is similar to similar to the conditions that you had in special theory of relativity, right? And so you are in a deep space away from gravitational forces, and at the same time, you are undergoing a constant upward acceleration. So the elevator is moving upward. However, you are in a deep space, right? Now, what will happen at this particular situation is, think about yourself that if you were inside this elevator under this condition, what you will feel is a force pulling you down. So this should be actually pulling. So let me. Right. A force pulling him down. If he drops a ball, it accelerates towards the floor as if it experiences a gravitational force, right? Now, this is what will happen if you are in an elevator in a deep space away from gravitational forces, but you are undergoing an upward constant acceleration, right? If when this happens, what you observe is you will feel a force pulling you down, and think about you dropping a ball in that elevator. So what will happen is it will accelerate towards the floor, as if it experiences the gravitational force. Even though you are not in the gravitational force, you will experience the similar thing, right? The ball will drop down to the floor. And that is the second scenario. And the third scenario is the elevator is near the Earth's surface, but in free fall, right? So now again, the elevator will be near the Earth's surface, but in free fall. Right? So which means it will fall freely. And at this particular situation, if you were inside the elevator, what you will feel is the weightless, as there is no force pulling you down, right? I hope that all of you probably have experienced this part at least. If you have used an elevator, which means if the elevator is in free fall, you will not feel your own weight, right? So you will feel weightless because there is no force pulling you down, right? And I guess all of you can understand that particular situation. Now, if you drop a ball, what will happen is that it will hover in the mid-air. So because you are on the free fall, the ball is also in the free fall, so it will not feel this gravity, right? So it will just hover in the mid-air without falling onto the floor, right? So this is the third scenario. And if you go into the fourth one, the elevator is again in a deep space away from the effects of the gravitational force. However, this time it moves with a constant velocity, right? So if you have an elevator, and again, you just think about it's in a deep space, but there is a difference now with this situation compared to this situation 2 that we discussed. That is, you are in a deep space away from the gravitational force. However, in this particular time, you move with the constant velocity, right? So you move only with the constant velocity. Now, if you move with the constant velocity, then the observer again will feel the weightlessness again. And if you drops a ball, it will hover in the mid-air again, right? So this is what can happen even without the gravitational force. Now I have discussed with you 4 situations here. Number 1, 2, 3, and 4, right? Now there are 2 situations that are equivalent to each other, and there are another 2 situations equivalent to each other. Now, can you comment on this? Which situations are equal to each other in these 4 scenarios? You can just tell equal, either 1 equal to 3 and 2 equal 4, or 1 equal 2 and 3 equal 4, like that. So just post your answer in the chat window if you do not wish to talk. So let's see whether you have understood this for particular scenario, right? So what we are trying to do is trying to understand the Einstein's principle of equivalence. So which two sets are equal here? Is it 1 equal 2 and 3 equal 4? Is it 1 equal 3 and 2 equal 4? Like that, or 1 equal 4 and 2 equal 3? So just comment how you understood about it. So I will wait until I get an answer from you, right? So the four scenarios are on the screen, so you can just read through and tell me or type here which two are equal. Right, I got one answer, and who else can answer? You can just tell only one answer, like one equal to 4, one equal to 3, which means the other two will be automatically equal to each other, right? According to our discussion. Right, so I have two answers, and in fact, three answers. Right, so I got few answers, so let me see. Now, the answer is actually straightforward here. I guess me and Nirmal, both of you got both of your answers are in fact correct, right? And so here are the two situations, right? So there are two notions of equivalence here. The first one is constant acceleration is in deep space is equivalent to being in a gravitational field, right? So that is the number one. So what that means is the constant acceleration in deep space means this one right here, number two, the elevator in deep space with away from gravitational forces, but is undergoing constant upward acceleration. So that is one scenario, and that is equivalent to being in the gravitational field, right? Now the other one is the elevator is resting on the surface of the earth, which means you are on a gravitational field, right? So that's why I have mentioned here that observer would experience the gravity pulling him down. So basically, even though these are two different situations, that the elevator is resting on the surface of the earth and the other situation is elevator in the deep space away from the gravitational forces, what you feel is the same, right? So that is the idea, 1 and 2. So which means we can tell that the first scenario is you just in an elevator resting on the surface of the earth under the gravity. So which means that is first one, and the elevator is in deep space away from the gravitational force undergoing a constant upward acceleration. So which means constant acceleration in the deep space, that is number two, is equivalent to being in a gravitational field. So that is number one, right? So 1 and 2 are basically kind of similar. You experience the same thing, even though it's two different situations, right? So that is one equivalence. And the other one is uniform motion in the deep space is equivalent to being in a free falling gravitational field, right? So that is number 3 and 4. Similarly, number 3 tells you the elevator is near the Earth's surface but in free fall. So which means you are in a free fall and you don't feel the weight. So you are in that situation where you feel the weightlessness. And similarly, if you are in a deep space away from the gravitational forces and moving with the constant velocity, again, you don't feel your weight. So observer feel the weightlessness again, right? So because of that, number 3 and 4 are equivalent. So that's number 2 here. Uniform motion in deep Minkowski space is equivalent to being in a free fall in gravitational field, right? And I hope you can understand this now. Now, based on this thought experiment, Einstein made two conclusions from this experiment. So this is not a real experiment actually that he did. This is just a thought experiment, right? The number 1 conclusion is gravity is an aspect of the geometry of space-time, not of the composition of an object moving through the space-time. Right. So his first conclusion was gravity is an aspect of the geometry of the space-time. Right. So that is number 1. And the small regions of the space-time are locally flat and should be special relativity. So change that. And the special relativity applies. And I think we have discussed that before as well. The laws of physics in a uniformly accelerating frame is same, should be the same as in the frame in gravitational field, right? And this is actually what we call as the equivalent principle in general theory of relativity, which is the important one. The laws of physics in uniformly accelerating frame is same delete this one. Should be same as in frame in a gravitational field. Right? This is the equivalent principle, and this is what we have discussed in this thought experiment under number 1 and 2. Right? Being in a gravitational field is same as that you are being in an accelerating frame, right? So that's the idea of these two. Right? And this is actually what we call as the equivalent principle, this last one, right here. And I have mentioned it here as well. You need to go into in sufficiently small frame of reference, the physical behavior of objects in the gravitational field cannot be distinguished by an experiment from uniformly accelerating objects, right? So what that means is if you are in a gravitational field, behavior of an object in a gravitational field cannot be distinguished by an experiment from uniformly accelerating frame. It's basically again says the same thing, being in a gravitational field and being in an accelerating frame, in a uniformly accelerating frame will be the same, right? So that is the idea. Actually, if you remember the last video that I showed you, this is what Einstein has expressed as his happiest thought of his life, because this was kind of the basic idea that he had initially to derive all this theory of general relativity. And he claimed that for an observer falling freely from the roof of the house, the gravitational field does not exist because it's in a free fall. And actually, this is due to the fact that, as you know, that the acceleration doesn't depend on mass, right? I guess all of you know that from the Newtonian gravity. And this is the principle of equivalence. And apart from that, we have two other principles The second one is called principle of general covariance, and it's the note is missing here for some reason. Let me check that. Right, so let me, so I will add that into here the note, but the idea is the principle of general covariance means that, so when you have it, general covariance means that when you, for example, you have to have a tensor equation to explain this theory. The idea is that it should not change based on the coordinate system, right? So if it is valid for one coordinate system, it should valid for the other coordinate system as well. So that is the idea, right? So let me just have it here right now at the same time. So I'm going to write it form of the laws. Physics should be the same on inertial and accelerating frame. Right, so this is the general idea, but I will add a little bit more to this note. For the time, let me keep it like this, that the form of the laws of physics should be the same in all inertial and accelerating frame. And I guess you probably have discussed this in special relativity as well. The laws of physics will be same like in all inertial frame, but I have add here the inertial and accelerating frames as well. And the idea is if you so if you have this the other idea that you need to understand here is if you take a physical equation for the general relativity, if it is true in one coordinate system, then it has to true in the other coordinate systems as well, right? Now, if you go back to your notes, and this is why actually we are using these tensor equations, because the tensor equations are coordinate independent. So it generally valid for all the coordinate systems, right? So this is why actually we have to use these tensor equations, right? Just go back to the previous notes. I have mentioned that before. And then the third principle is the principle of consistency. So what that means is that under appropriate conditions, the general relativity law should reduce to both the laws of Newtonian mechanics and also in the absence of gravity to the laws of special relativity, right? And I guess in special relativity, you probably have done this as well when you derive the theory of special relativity. When you have, speeds that are sufficiently small compared to the speed of light, you should be able to derive, you should be able to show that the Newtonian mechanics is still valid. Right? So the same thing applies here under the principle of consistency. Once you derive this theory of general relativity, you should be able to show that it will reduce to Newtonian mechanics under appropriate conditions, right? Now, in particular here, if the gravitational field is weaker, then you should be able to show that this the theory will reduce to, the general theory will be reduced to the Newtonian mechanics, right? So we are going to show it at the end. So that these are the three key principles that we are going to use to discuss about the Einstein's field equations under general theory of relativity. Once again, the principle of equivalence and the principle of general covariance, and the third one is principle of consistency, right? Now let's look at some of the things that will be useful for us to derive this theory of general relativity. Now these are some of the things that we have already discussed. The first one is you can model the time using a 4D Riemannian manifold. However, in small regions of curved space-time, we can construct a Cartesian coordinate system with the metric tensor, as you can see here, right? And so I'm not going to explain this too much because we have discussed this already. And the second thing is under the principle of general covariance, which will it will allow us to take a valid tensor equation from special relativity to general relativity, right? So as I told you, according to this principle of general covariance, you can take a valid tensor equation from special relativity, and then we can convert it to the general relativity, right? Now to do this, we have to replace the Minkowski metric with the general metric tensor, right? The Minkowski metric is neta mu nu right here for the flat space, and we can replace that from a general metric tensor. And the other thing is you can replace the partial derivatives with covariant vectors. And there is we also tell the same thing as the comma goes to semicolon. So that means the comma and the semicolon can be used to as a shorthand notation for partial derivatives and covariant derivatives, right? Now, how to find these covariant derivatives? We have done it in the previous lecture. Just go back and look at it. And if I can get it here, yes, this under lecture 4, if you remember that we discussed how to find these covariant derivatives right here, right? And this is where we learn about connection coefficients and everything. So make sure that you go back to this note and look at it if you can't remember what we have done. Now, for the proper time in special relativity, we use c squared d tau squared, and it can be written using this metric in the Minkowski space neta mu nu, right? Now, in the curved space in the general relativity, we, in terms of having this matrix right here, we replace it from g mu nu, right, with the general metric. Right, so this is called Minkowski metric, but that only applies for flat space-time in special relativity. But under the principle of general covariance, you can take this and replace it by G mu nu, right? So that's what we have done here. Now, some examples for this covariant differentiation or this rule called comma goes to semicolon, we can write now the law of conservation of particles in special relativity. We normally write it in this way, n times u alpha, and there is a comma to represent that partial derivative. And this is same as writing in w alpha over w x alpha, and this is equal to 0. And this is called law of conservation of particles in special relativity. And if you need to write the same thing, by the way, this u alpha is the 4 vector velocity, right? So I am assuming that these things you probably have understood under the theory of special relativity, right? Maybe not in the same format, but you probably should have an idea like 4 vectors and all these things. And for the general relativity, you can write the same thing, just replacing this comma by a semicolon right here. So that's a notation. Or else you can write n in terms of having a semicolon, you just can write red alpha, u alpha right here. Right? So that's how you write the same thing under the general theory of relativity. Right? Now the conservation of 4 momentum in special relativity, you use write it as T mu nu, comma nu. So that means again, so this part right here, comma and nu represent the partial differentiation, that is dabba T mu nu over dabba x nu, which is equal to 0. And the same thing can be written in general relativity, just replacing this comma by a semicolon, right? Or you can write that mu, T mu nu, which is equal to 0, which is the conservation of momentum, right? Now, this tensor right here, T mu nu, is called the energy momentum tensor. And this tensor is defined using this particular equation right here, which is called as energy momentum tensor. Now, this is one of the important tensors when deriving Einstein's field equation, and because of that, we are going to discuss about that particular tensor in detail to see what kind of a tensor that is. And here is the components of the energy momentum tensor. Now in a 4-dimensional space, this particular tensor has 16 components in it, and all these components represent different things, as you can see in this diagram. T00, the first one right here, is called the energy density, and then these 3 components T01, 02, and 03 represent the energy flux, and then these 3 components right here, T10, T20, and 30, so they represent the momentum density. And then this part right here, all the off-diagonal elements, which is from this pink color, T12, 13, and 23, and 21, 31, 32, all these off-diagonal elements represent shear stress, right? And the diagonal elements from the green color, they represent the pressure, right? Now you can see that this particular tensor, the energy momentum tensor, has a lot of information inside it. Now let's look at briefly what all these components means. Now you have 16 components here. Now if you take one by one, T00, So that is this first one, the energy density. So that represents the flux of zeroth component of the P mu. P mu is the form momentum across the surface of T equal constant, right? And that equals to energy density. And then Pi0 is the flux of ith component of the P mu across the surface of T equal constant and equals the momentum density. So that is these three values. Ti0 means it can be 1, 2, or 3, 1, 0, 2, 0, and 3, 0. All these three components represent the momentum density. And then 0 I component, those are the these three components right here. So those components represent the energy flux again. So that is the flux of energy across the surface of xi equal constant and equals to energy flux. Right? And then these diagonal elements 1, 1, 2, 2, and 3, 3, which I have represented here from Tij is the flux of I momentum and equal to where I equal J and shear stress when I doesn't equal to J, right? So the idea is when you have this, for the diagonal components, when I equal to J, so that is pressure. And when I does not equal to J, all the other components are actually belongs to the shear stress, right? Now let me just explain briefly physical meaning of these fluxes by using this diagram right here. So I use a simple system where you have non-interacting particles, which means the particles do not interact each other. Each particle with mass m moves with a common velocity v. So each particle, as you can see in this diagram, will move with the common velocity called v, and it has two components, vx and vy. So for the time being, we assume that we do not have a z component, just to make this understand. And then there is a shaded area, that is this area right here on this side. And we have a parallel height right here, and that area that I have shown here, AB is right here, and then you have this area, right? Right, so let me take these numbers right here. The total relativistic energy of a particle is E equal gamma mc square, right? So that is assuming that the relativistic energy, you can write it from this equation. The gamma is this Lorentz factor, as you know from the special theory of relativity. And if you think about, there are n particles in a unit volume, the total energy will be n times gamma mc squared, right? If the energy of one particle is gamma mc squared, and the number of particles per unit volume means n, then this will be n times gamma mc squared, right? Now, if you go back to this component right at T00, that is energy density, right? So that should be energy per unit volume, right? Now this is the energy for unit volume. When you have an energy of a particle multiplied by a number of particles per unit volume, that is n times gamma mc squared, that will give you the energy density, right? So that energy density is that first component, or the T00 component of this energy momentum tensor. And because of that, the value that should go right here is n times gamma mc squared, right? So that is an example to how to understand this tensor. Now, if I assume all these particles have passed through the shaded area, which is perpendicular to x-axis. So in this diagram, you can understand it clearly. The second one here is the x-axis, and this shaded area is the area which is perpendicular to x-axis, right? And if you think about, all particles will pass through this shaded area A within a time t, then what you have as the number of particles is n Vx A times t. Right? So I hope all of you can understand. Right? So you have a shaded area A, and so n is the number of particles per unit volume, and the volume that it contains is A times t is the the total volume, right? So Vx is the velocity, and once you multiply it by A times t, A is that area, and then you multiply it by time, what you will get is n is the number of particles per unit volume, and then you multiply it by this whole value right here, which will give you the number of particles, the total number of particles that will pass through this shaded area in a particular time called t. Right? And so if you take the total energy of all these particles, as you can see that energy of one particle is gamma mc squared, right? And you just need to multiply it by the total number of particles to get the total energy, right? So that means the total energy of all the particles are NVXAT, and you have to multiply it by energy of one particle. So that is gamma mc squared, right? Now let's look at T01. So that means this one right here. So the energy flux, which means you have to find the flux again. So that is the total energy. And to find the flux, you have divided by AT times C, right? And then you will get NMV x gamma C. So this is the energy flux that you get as T01, which is this component right here for the x direction, and for the 02 and 03, you will get y and c components similarly. So if you do the same calculation towards the y-axis, you will get NMVy gamma c, as you can see here, like that. If you have the c components, then you will get NMVc gamma c, right? So that is if you have the c component, but for this particular time, I have assumed that the c component is 0. In the similar way, you can also calculate the other components towards the other direction, T20. So that will come as N gamma Vyc, which is actually similar to T02. And T10 also equal to T01 as well. Right? And if you have had the C component, then you will have a T30, which is Nm gamma Vc. Right? So which means you will get these components right here and the components in the first row, except the very first value right here, which is the energy density. But you can calculate these three components and these three components in this way. And similarly, just so I have mentioned here how to just to get an idea about the other components as well. And once you do all these calculations, you can take a value for each component of the tensor, right? And that will be the first one will be n gamma mc squared, which is what we have done here, n gamma mc squared. And then this component right here, n gamma vxc. So that is this component right here. And that component and this component will be similar, n gamma vxc. Like that, you can calculate each and every component, and I have mentioned here how to get an idea about the calculation, right? So if any of you cannot understand it just by reading it, then let me know. Other than that, I have mentioned how to do the calculation, right? And actually, we are not going to discuss this in detail, but so what you want to get here is just to get a feeling. What is this energy momentum tensor, and what kind of values that you have as components, right? So that's why I gave you a description, because we are going to use this energy momentum tensor to derive the Einstein field equation, right? Because of that, it is always better to have a rough idea what kind of components that you have here. So basically you have energy flux, momentum density, momentum flux, and something called shear stress and the pressure, right? And then you have the energy density right here. Right, so let me quickly go into the next section. Now assume that you have all the components in this energy momentum tensor. And then this is the general form of this energy momentum tensor. And we are going to discuss two special cases of this. The number one is called the dust, and the other one is called perfect fluid, right? So those are the two special cases that we are going to discuss. So actually what we are going to do is, you can see that this particular tensor has all the 16 components, and what we are going to do here is, under these special cases, we are going to reduce the tensor. And if you think about the dust, so what that means is a collection of non-interacting particles which are at rest with respect to each other, right? Now, why we are discussing about this situation is that in cosmology, we can use this condition about the dust as a good approximation for a matter-dominated universe, right? Now, there is a section actually we are going to discuss in some of the lectures within probably next few weeks. That is, there are two different universes that we can discuss. One is called matter-dominated universe, and the second one is called radiation-dominated universe, right? We have not discussed those two. And actually, we are now in the matter-dominated universe, but when you go back to the beginning of the universe, there is an area where there is a time that we call that we have a radiation-dominated universe, right? And we will talk about those two. Actually, to talk about that, we first need to derive the Einstein equations, and then we have to go into the cosmology part, where we are going to use something called Robertson-Walker metric, and then we have to use derive something called Friedmann equations, right? So we will do that part, but for the time being, just understand that there are two different types of universes: the matter-dominated universe and the radiation-dominated universe. Now, this condition about the dust that we are going to use is a good approximation for this matter-dominated universe, right? And under this, in this situation, our energy momentum tensor will be reduced to a very simple one, right? And we can discuss about the matter-dominated universe using that particular tensor. So that is the idea. Now, the idea is that when you have this, when you have the dust, we can consider a small region of a dust cloud as a fluid element which contains particles with approximately equal average velocities. So that is the idea, right? So when you use this condition, you can consider a very small region of a dust cloud as a fluid element, and it will contain particles with equal average velocities, right? And if you consider a Lorentz frame containing this homogeneous region, we can consider this as a momentarily co-moving rest frame of the fluid element, right? Now, when these dust particles are at rest, we don't need to have any velocity because they are at rest now, right? When the dust particles are at rest, and also gamma will be equal to 1, because now the particles are at rest, what will happen is all the velocities will be 0. So, and because of that, you can see that in this energy momentum tensor, all these components have velocities, right? Except this first component T00 right here. And because of that, under this condition, when you consider the dust, you can assume that all the other components will be 0 for the energy momentum tensor except this one right here, the 0 component, right? So what is important for you here is actually to remember and understand these two conditions, right? So what happens under specific conditions for the energy momentum tensor, right? So these derivations that I have here is just to give you a feeling about the energy momentum tensor, that what kind of things that you have inside, right? But what is important is when you have the energy momentum tensor, how to reduce and use it under these two conditions, right? So when you have dust, all the components will be 0 except this particular component right here. And here also what you had was n gamma mc squared, but since all these particles, you have the velocities are 0 as the dust particles are at rest, you can take the gamma equal to 1. And then what you have is nmc squared, and also nm you can write as the mass density, right? Rho equal nm. So you replace this term with rho c squared, and all the other terms are 0, right? So that's what has happened, right? Now that is one scenario. And the other thing is what happens when you have a perfect fluid, right? So there are 3 conditions that you can apply for a perfect fluid. And this is also used to model different systems in cosmology, including the universe, right? And the perfect fluid can be used as perfect fluid. Normally we used to tell that it has dust plus pressure, and it has a 0 viscosity, and it has a 0 heat conduction. And once again, what we are doing here is actually we have this energy momentum tensor, and we are using 2 specific conditions here. Under those conditions, we try to reduce this energy momentum tensor to a simple one to use in different models, right? So that's what we are doing here. And the first one right here is dust. When you have dust, you can see that all the velocities are 0. So you will have only this component right here. So when you use it, it will be easier for the calculations, right? In the same way, when you have a perfect fluid, what you have is dust plus pressure, and you have a 0 viscosity and a 0 heat conduction. Now, as a result of these 3 conditions, we can again reduce this energy momentum tensor to a simple one. That is, when you think about the viscosity, it is actually a liquid friction between two particles, right? And because of this condition right here, which means if you have a zero viscosity, so that means this liquid friction between particles should be zero, and this will affect to the shear stress, which is Tij components when I does not equal to J, right? So which means if you have a zero viscosity, these components will be zero, because that you do not have friction between two particles. We assume that we do not have a shear stress. So that means if you go back to this particular tensor, all these components are related to the shear stress, right? So those components will become zero, right? So that's what I have mentioned here. So that is one condition. And the next one is, though the particles do not move in MCRF, MCRF means momentarily for moving reference frame that we have discussed earlier right here. So normally in this frame, particles do not move, right? However, the energy can still transfer through the heat conduction, right? I mean, there are two ways that you can think about energy can by moving the particles. The second one is the energy can transfer through the heat conduction. Even though you consider this momentarily for moving reference frame, energy can still transfer through the heat conduction. But we have assumed here that in a perfect fluid, there will be zero heat conduction, right? Because of that, there will be no heat conduction. And as a result of that, these components will be zero, Ti0 and 0I components, because these movements of energy associated with the momentum explains by Ti0 components, right? So that's how you understand it, because if you go back again to this, you can see that here is the momentum density right here, and then you have the energy flux right here. So always there is a yes, the velocity involves, right? The momentum involves in these components, which means when you have a zero heat conduction, these components will also be zero, Ti0 and 0I components, right? So at the end, what you will have is only the diagonal element of the matrix, right? So once again, for the dust, you have only one component for the energy momentum tensor. But for the perfect fluid, what you will have is only the diagonal elements, right? And I guess there is should be zero for I equal J. That should not be equal to zero, because what you have zeros is under the zero heat conduction and zero viscosity. Other than that, you should have dust plus pressure both in the energy momentum tensors, right? So you can see that the pressure is represented from this diagonal element. So which means this diagonal element should be there with the energy density. So what you should not have is these shear stress components and the momentum components. So let me check this. I think it should not be zero. Yes, so it says PHY equal to 0 for does not. I think this is actually not correct. So this should be TII equal to P, which is the pressure. Right, because TII is the diagonal element, both of them should be equal to each other, and that should represent the pressure, right? And because of that, you should have only the diagonal matrix, right? P rho C squared, and then 3 P's right here. And we can write this energy momentum tensor for a perfect fluid in this way: P rho plus P over C squared U mu U nu minus P neta mu nu. And this is actually how you write it in the Lorentz frame and using the Minkowski metric, but using the principle of general covariance, you can convert the same to the general relativity. All you need to do is replace this neta, which is the Minkowski metric, from the general metric tensor, which is G, right? Now, also under this condition, if the pressure is so small compared to the rho, what will happen is this term right here will go away because the pressure is so small. And then this part P plus rho plus P over C squared, this part will also go away, which is again the pressure. And that once that those two will go away, what you will have as energy momentum tensor is rho U mu U nu, right? So this will be the final energy momentum tensor you have if the pressure is smaller, right? Considerably smaller compared to the density rho. And that's how you can reduce this energy momentum tensor under the two conditions that we have. And in the next section, actually, that we have to discuss is about the Einstein's field equations. Now we know all the tensors that we need to understand, which are Riemannian curvature tensor, Ricci tensor, and Ricci scalar, that will come into play in the Einstein's field equation in one side, and the other side would be this energy momentum tensor, right? And different components of the energy momentum tensor we discussed today. And at the same time, this is the general form of the energy momentum tensor, and we have discussed two special cases, that is where when you have dust and when it is when you have a perfect fluid, right? So these are discussed for a reason, because we are going to use these two conditions at two different situations to discuss different cosmologies and different modules, right? Now, under the dust condition, when you have dust, it's a collection of uninteracting particles which are at rest with respect to each other. When these particles are at rest, the general idea is all these velocity components will go away. And what you will have is only this component right here. And since they are at rest, again, the gamma will go into 1. And then n times m is the mass density, and you take that as rho, and your energy momentum tensor will be reduced to this one right here, right? Only one component is there. And the other condition is that when you have a perfect fluid, there are three conditions. You have dust plus pressure and zero viscosity and the zero heat conduction. And because you have a zero viscosity, what that means is all these shear stress components will be zero. So that means all these Tij components will be zero for I does not equal to J, right? So those are the off diagonal components. And what you will have at the end is only the diagonal components. This component right here that you will have, and then since you have the pressure, you have all these diagonal components for the matrix, right? So it is very important that you remember these two conditions, which will come again and again. And this part right here is just for your understanding how the meaning of all these components, right? But what is important here for the time being is just to understand and get the basic idea how this energy momentum tensor looks like, and then how you can reduce it to these two situations, because we are going to use that at different times, right, to solve these Einstein equation. Right, so I guess so I went through it a little bit faster, but most of these things are related to what we have done previously. Now on the next day, what we are going to do is we will discuss about the Einstein field equations, how we can derive it, and how Einstein's, rather than directly giving you the equation, I will discuss actually how that Einstein approach to this equation, and at the end how he derived it, right? The Einstein equation, and we will also talk about the Einstein tensor, which is just a different form of what we have done, and there is a cosmological constant that he has added at the end for the equation, and we will discuss this part on the next day. Now, anybody have any questions up to here?